Looks like we're there. Welcome back, everyone. So for today's class, we're going to be just working through section 7.5. We may not finish that section. We're never in a rush to finish them. We'll see where we end up on this one. The bigger announcement is that next Monday, we'll have our third 50-minute exam. Like the others, it's based off three sections, sections 6.3, 7.1, 7.2. And 7.2 is the section that's due today. If you don't have it quite finished, I'll accept all work late for full credit. So the first thing you should do to prepare for the exam, this is a comment I duplicate a lot through that semester, is get caught up on those three sections. I'll get them graded, sent back to you as soon as I can once I receive them. Then once you're fully caught up with homework, that'd be a good time to turn around, look into these two versions of the sample exam exercises for extra practice. Anytime you're studying, good thing to do right away is just write down the unit circle diagram, plot all the angles, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, and so on, all the way around the unit circle, just as a great warm-up. Then practice memorizing these identities as well. Just start writing them all down, the addition formulas, sum difference identities, the double angle formulas, Pythagorean identities are going to be the major ones. That's a short spiel of enhancements. Any questions or comments at the moment, folks? Okay, well, like the other exams, it's quite a short one, only because 50 minutes is not a lot of breathing room to get everything down on paper. I try to write an exam that's even shorter, probably about, in reality, a 40-minute exam is what this is, with 10 minutes baked in as just extra time to check your work. 6.3, just the standard problems that we did on inverse functions. You're just doing a bunch of evaluations. It's kind of like on exam one, where there's one page, you had to calculate cosine, say, pi over 6, tangent 2 pi over 3, just a bunch of inverse function evaluations now. There'll be two problems in 7.1. First problem is going to be just simplifying something down. Second one is going to be verifying that an identity is a bona fide trigonometric identity, but nothing too crazy. So this one will be pretty straightforward. And 7.2 is just going to be using the sum difference identities. So two problems there. So that'll round up to our third exam. After that, and after section 7.5, we're going to be moving into chapter 8, applications of trigonometry. So it's kind of, in a certain sense, looking into some of the fun stuff now that we have all of the major tools under our belt. But I guess that's my full set of announcements. Any questions or comments at all, folks, to start us out today? Okay, well, here's where we left off. We didn't get too far in section 7.5. In fact, we only solved one equation. We mentioned first just some notation. We're focusing on this bold letter Z here is a great symbol for mentioning the set of all integers. And we need that because we use periodicity when we are trying to find all solutions to a trigonometric equation. The idea was if you have cosine x is negative root 2 over 2, then we just go to negative root 2 over 2 on the x-axis, find the angles that makes this true, and you can plug these in. 3 pi over 4, if you take cosine of 3 pi over 4, it checks as negative root 2 over 2, and same as at 5 pi over 4. But in order to find all solutions, we notice that cosine repeats with period 2 pi. So if you put in a solution right here, like say 3 pi over 4, add 2 pi times k, or k is any one of these integers, you get another solution. So now there's infinitely many solutions to these periodic functions. The moment we found at least one, we found two solutions between 0 and 2 pi. So now this is two infinite lists of all solutions to the trigonometric equations. There's lots to talk about when it comes to these trigonometric equations, so we have 6 more examples to look through. But any questions on this warm-up, what we did last time? Okay, let's try it out all over again. For the new equation, 2 sine 3 theta plus square root 3 equals 0. Feels more involved. There's lots of stuff on the left-hand side. The input to the trig function is not just x or just theta. It's 3 theta this time. But it's really kind of the same idea as before. What made the last equation solvable was the trig function itself was alone on one side. So step one is to isolate the trig function. And that's not too bad. We can subtract square root 3. So 2 sine 3 theta is now negative root 3. Divide by 2, sine 3 theta equals negative square root 3 divided by 2. And now we just go to the unit circle and find where 3 theta can come into a negative root 3 over 2. So step 2, find angles on the unit circle. Seems like a lot of the work we've been doing somehow, some way boils down to this kind of diagram. So here's the unit circle brought back. The value that we're going to place on it is now on the y-axis because we have a sine function. Negative root 3 over 2 is way down here, close to negative 1, about negative 0.9. And this gives us two particular angles. One of them is this angle right here. This one is going to be 5 pi over 3. Another angle is over here, and this one is the 4 pi over 3 angle. And you can check, if you swap 3 theta, the entire 3 theta, for 4 pi over 3, you do get negative root 3 over 2. And same with 5 pi over 3. So we found two main solutions, pretty much just mirroring the last problem. The only difference is this time we have to say 3 theta equals both of these values. So this now implies 3 theta, so strange looking theta, let's correct that, is equal to 4 pi over 3. The story isn't over, so I'm going to put plus here and come back to it. Or 3 theta is equal to 5 pi over 3 plus, and then this is where we involve periodicity. Step 3, use the fact that sine has period p equals 2 pi to find all solutions. So we're going for this targeted part of the instructions. We're using the period 2 pi, and all we have to do is say, if 4 pi over 3 is a solution, rotate by any multiple of 2 pi, and you land back at a coterminal angle. So this would be plus 2 pi k. K could be positive 1, it could be negative 1,000,000, it just has to be an integer. So this gives us all solutions using periodicity, adding on k, so 2 pi k here as well. And it's nearly completely solved for, except when we solve for an angle theta, the idea is theta itself has to be completely isolated. So last step we take is just take both of these equations here, divide them by 3. So the solutions to this original equation goes theta equals, divide by 3 here, gives us 4 pi over 9, plus 2 pi k thirds, or do it again on this one, divide by 3. Theta equals 5 pi over 9, plus 2 pi k thirds. And let me correct some of my penmanship there. Whenever you introduce a new symbol out of nowhere, it's always a good idea to say, what is it? What is the domain of the symbol k? So we'll say here, where k is any integer. And just to call out that shorthand once more, you could just say k is in z, the set of all integers. I'll usually just write it out. I think that's a clear way to say it, just ordinary words. But we did it, folks. This equation fundamentally is the same as example 1, except we had to solve for the trig function. Then, after we found the two particular angles between 0 and 2 pi, that gets us to negative root 3 over 2, we just divide by 3 and we have those solutions. So the added complexity here was all kind of fluff in a certain sense. Following this process, we still have the same kind of solution set, just like on the last example. Well, that's 2 down. Any questions at the moment solving this one?
Why did it become 4 pi over 9 and 5 pi over 9 instead of over 3?
Oh, when I divide by 3 on both of these lines here, it
Oh,
would
I
look
see.
like this.
Yes, I
Yeah,
see
pretty
now.
much everything got or divided. It's rather. Other questions at the moment? I feel like I should fill this out as well, just for clarity. Okay, so this is the main kind of wants we are trying to go for when we solve a trigonometric equation. We want to have one trig function if we can get it, then try to isolate that trig function. Whatever is inside is okay. It just carries over down here, and then we solve for that angle. But when it's more than one trig function, we definitely have something new. There's a bit of a problem with this one. 3 tangent squared minus secant squared minus 5 equals 0. This one is not easy to solve if we're handling two trig functions simultaneously. But that's okay, because we could just use a Pythagorean identity to eliminate one or the other. I think the easiest one to eliminate on this problem might be secant squared, but you could also eliminate a tangent squared, right, in terms of secant if you prefer. So the identity I'm thinking about on this one is secant squared x equals tangent squared x plus 1. This is just one of the Pythagorean identities. I wrote it in a different order just to emphasize the way we're going to substitute. So using this idea, the secant squared here becomes tangent squared plus 1. And we get the first thing we would like to see when we're solving a trigonometric equation. Now there's just one trig function. It's just in multiple places. So this turns into 3 tangent squared x minus, make the substitution, secant squared is tangent squared x plus 1 minus 5 goes to 0. Next, we'll distribute the negative into that group, combine like terms. So we have 3 tangent squared x minus tangent squared x minus 1 minus 5 equals 0. So altogether, it's 2 tangent squared x minus 6 equals 0. So now the dust is settled. There's one trigonometric function. And at this stage, it's really no different than example 2. Example 2 had, well, a sine function of 3 theta, a combination of it. We have tangent squared this time, but we can still isolate that trig function. Let's add 6, divide by 2. In stages, 2 tangent squared x is positive 6. Then tangent squared x becomes 3. It's still not completely isolated. We just need to take the square root. But this is where this identity that we discussed way back, I believe in section 5.2, comes into play again. If you take the square root of anything squared, a can be a tangent, for example, squared, you get the absolute value of that thing, which means there's really two answers. Another way to visualize this is if you have a squared equals some constant k, and you go to take the square root of this, you would have a equals positive or negative root k. So squaring this side right here would get you back to the top. The reason there's two versions is because the square root of a squared on the left is really an absolute value, which splits into a positive version and a negative version. So same issue right here. Take the square root of tangent squared, and you get that tangent x is positive or negative square root of 3. And a quick way to think about this is square both sides of this equation. The square of this, whether it's positive or negative root 3, gets back to 3. Square of tangent gets you back to tangent squared. That means there's really two equations we have to solve now. This is something new that we haven't seen in the last examples. We need to solve simultaneously that tangent x is negative root 3. And the second equation, tangent x, is positive root 3. But really, it's not too bad. We can go back to the unit circle here, find good candidate angles, but there's something new and special about this problem again that's different from the others. When we're dealing with sine, cosine, secant, cosecant, which is just the reciprocal of sine and cosine, period is 2 pi on every one of those. But the moment you go to a tangent or a cotangent, you're in a different kind of reality. Period of tangent x is p equals pi. And that's a really helpful observation because it tells us if we're going to find all solutions, really, we only need to look from 0 up to pi. This is the whole space we need to find those solutions on. And any solution we find here along this band, the upper portion of the unit circle, we'll just add pi times k to it using periodicity and get the next solution. So that saves us a lot of trouble. You don't have to look for every single time tangent is going to turn into a positive or negative root 3. There's 4 instances, but we can simplify it to just 2 cases. Let's take a look into these angles. One angle where this should work out is pi over 3. We should do a quick check on that. Tangent angle pi over 3 is going to be the sine value. And looking at this geometrically, sine value is close to a positive 1. That's the root 3 over 2. Divide by the cosine value, which looks like it's dead on 1/2. In fact, it is. This gives us root 3. So pi over 3 solves this equation right here. This would mean x equals, let's put an or in the middle, pi over 3 plus, and we'll come back to this, so let's just put a plus to remind us there's something missing. For the negative pi over 3, we can just go over here, negative square root 3, not pi over 3. To the negative square root 3 branch of the 2 equations, we can just rotate over here, go to 2 pi over 3. Do another quick check just to make sure everything looks right. Tangent 2 pi over 3 is same value for sine, positive root 3 over 2 again. But the cosine value is down here, negative 1/2. So that does check as a negative root 3 altogether. So from this one, we get x equals 2 pi over 3 plus, then we use the slightly different period here. On the other problems, when we were using periodicity, we went plus 2 pi k, and then this one had to be divided by 3. But because this time the period is pi, we just go plus pi times k on both. So this is the full solution set to the original equation at the very top. 3 tangent squared x minus secant squared x minus phi equals 0 means x is one of these 2 different values where you can pick any integer whatsoever for k. Pick them both 0, and you're just picking up these 2 main solutions that we found. If you picked k as 1 on pi over 3, you would rotate by pi and be down here. This is 4 pi over 3, and that also checks. That one would come out as a positive square root of 3. Add another pi to that, and you'd be back up to pi over 3 over here. So that's why we're just using a period pi. That's sufficient to get all solutions now. We'll just say where k is any integer. If you forgot to say this last part, I wouldn't dock you credit on that, no problem. But it's a good reminder, especially if you're going back to your work you did in prior. You would want to know what was k in the first place. So it's good to write it down just to reinforce that thought. So this one's definitely trickier. We had to use a trigonometric identity out of nowhere. That's the use of section 7.1, 7.2, 7.3. We also had to split this into 2 different branches, use a different period. So that was the use of our information on plotting these trig functions, knowing it had period pi. We'll try out a slightly more interesting situation on the next one as well. But any questions so far on solving any of these? Okay, well, so far examples 1, 2, and 3, instructions said find all solutions. We're just reinforcing the concept that a trigonometric equation by default has infinitely many solutions. But sometimes we're only looking for a specific set of solutions. So this is a common set of problems as well. Determine all solutions in the interval 0 to 2 pi. Sometimes those are just the main solutions we want, and that's where the equation solving would end. And let's take a quick breather before we solve this one and mention the homework is a little bit different for section 7.5. This is another one of those sections where I wrote down custom problems. So here's what it looks like. Similar kind of problems like we're doing in the notes. The reason I did custom problems on this section, where some of them are all solutions, other ones are like the ones we're about to try, is because the textbook does really a great job showing you examples in the reading of how to do this one, but there's none of these in the homework set. That's kind of frustrating. For some reason, they thought, we'll study how to do this, but we're not going to practice it in the exercise set for that section. So I made a custom set where we'll actually practice some of these as well. So if we're only looking for solutions at the interval from 0 to 2 pi, notice the interval notation. 0 is going to be a potential solution, but because 0 and 2 pi end at the same place, they're coterminal, a solution 0 is sufficient. We're not going to use a solution 2 pi. If we get a solution 0, we'll just state the 0. So the parentheses there say we kick out 2 pi itself. And here's the equation we'd like to solve. 8 sine squared x plus 6 sine x is 5. It satisfies one of our requirements. There's only one trig function here, so that's kind of nice. The other problem is, well, the trig function is in multiple spots. We saw that in the last problem. We had 3 tangent squared minus tangent squared. We could just combine like terms, and our job was done. Now tangent squared is in one spot. That's not going to work on this one. These are unlike terms, so it's definitely a new kind of problem. But here's the thought of this one. It feels more abstract than it really is. At its heart, it's just a factoring problem. You could rethink of this equation by analogy as you're looking into 8s squared, or x squared if you preferred, plus 6s, s to or minus, this is a sign equation, equals 5. If you were solving this as just an ordinary algebra problem where there's no trigonometry in the background, it's a quadratic polynomial, could use a quadratic formula, but standard thing is try to factor it first. It's often the fastest route to go. Subtract 5 from both sides. 8s squared plus 6s minus 5 is 0, and then just factor the equation. Factoring this one, a good try might be something like a 4s and an s. Signs are mixed if we go positive and minus. I'll just go plus and minus and change them if it's not quite right. But if prime number 5 is kind of helpful, that means you can either put a 5 here. Probably not a good idea because that would be a negative 20s if we put a 5 there. So let's put the 5 in this position and a 1 in that position. Our check is the outer product. This is 4s, negative 4s. And hang on, I had 8s here. I think we need a 2s right here, right? To make that come out as an 8s squared. That looks a little bit better. Now 5 times 2s gives us a 10s. 10s minus 4s gives us 6s. And so that tells us the factoring is successful. So if you can factor it this way, sure, it looks uglier in this form because there's more complexity when you're looking at a sine x, sine squared x, but the algebra is completely identical. Let's take the same steps. 8 sine squared x plus 6 sine x minus 5 is 0 automatically implies we have this factoring, 8 sine x. I'll just write as sine x this way without parentheses. 2 sine x. Let's go plus 5. minus 1, and that's automatically the right factorization. If it works over here, by analogy, it'll also work over here. Then next property we have is the good old zero product property. Yeah, question first. Oh, thanks for spotting that. To use this strategy, make sure you copy it down exactly. Thanks for seeing that mistake there. Other questions so far? Okay. Well, now that we have the correct factorization imported from the right, because we have zero, the idea is by the zero product property of real numbers, the only way something times something results in a zero is if the first thing was 0, 4 sine x, plus 5 is 0, or the second thing is 0, 2 sine x minus 1 is 0. So it splits into two equations, and we should expect that if it's degree 2, usually you're going to deal with two equations. That's exactly what happened in the last problem. It was tangent squared, and it in fact split into these two different equations. This is just a more built-up example of that. So now we have two equations, we've got to solve them both. But now it's like an example 1, example 2 problem. We just solve for the trig function on both of these equations. So isolate sign. On this one, subtract 5, divide by 4. Sine x equals negative 5/4. And as we write this down, think about how sine x plots. Way back in section 6.1, we were plotting the sine function, because that's suddenly pretty relevant here on this problem. Let's solve this one. Add 1, divide by 2. Sine x equals 1/2. So two equations to solve. But actually, if you're thinking about the graph of sine x, there's one equation to solve. This one is a bogus equation. And here's one way to think about it. If you plot sine x, here it is. It's a periodic function. Its amplitude is 1. The maximum value it takes is 1. Minimum value it takes is -1. That makes the negative 5/4 really kind of suspicious as a right-hand side. If you plot negative 5/4, that's less than -1, and there are no intersections on this graph. You get solutions when things intersect. So we can solve this one at 1/2 because 1/2 is right here. We're not going to get the infinitely many solutions because we're constrained to 0 to 2 pi, but we'll get some solutions. Looks like it's these two we're looking at right here. That tells us the negative 5/4 is no good to us. No solutions here. Not bad in a way, that just means less work to do on this one. So there's a lot of ways to convey this. First, let's say there's no solutions. Right, kind of small because it's not the overall conclusion. This one has solutions. There's no solutions over here because one way to say it is sine x. No matter what, dealing with the real number system, it's constrained between +1 and -1. Or another way to say it is because sine has amplitude a equals 1. So if you go beyond -1 or +1, if this was a 4, for example, same exact problem, no solutions. So that's kind of nice in a way. We could just move over to solving this one. Sine x equals 1/2. Any questions on the process to this stage? Okay, well, we want all solutions to sine x equals +1/2. We're only looking in the interval from 0 to 2 pi. So here's what the graph looks like this time. Going from 0 up to 2 pi, where 0 is included with the bracket, 2 pi is excluded, but we put it here as the boundary point regardless. We have a half that we're dealing with, so we could plot 1/2 on the y-axis. Here it is. And reverse engineering to what the angles would be means go to the right, go to the left, And here are the two angles. One of them is pi over 6. The other angle over here is 5 pi over 6. So we can solve this pretty cleanly. There's two different values, pi over 6, 5 pi over 6, and our work is done. Those are the only two angles that will result in a positive 1/2 from 0 all the way to 2 pi. There's just nothing in quadrant 3 where it terminates, nor quadrant 4. So last thing to say is x equals 5 pi over 6, comma, pi over 6. And we did it, folks. This one feels a lot more complicated because of the factoring involved is not straightforward to look at. It's algebraically the same ideas here, but feels like a lot's going on visually. But then we split to two equations. We use geometry to exclude or to make the big conclusion, no solutions here. And we use the different unit circle geometry to find the other two solutions. So they're pretty busy problems, but the more you practice them, the more they come together. I would say the reading in section 7.5 is really good. It gives us lots of different examples to take a look into. So give those a practice as well when you're doing the homework, and it's a big help. But any last questions at the moment? Getting through this one? Okay, one question you might have is, why haven't we used so far an inverse function? And it's a great thought because when we go down to these, I put in red the rounding information, so there's a small revision on the notes. But when we go to solve these equations, we're going to use an inverse function because we're getting stuff like -9/5 or -5/9, and those don't readily lead to nice angles like we've been finding before. The other reason we've been avoiding inverse functions is it kind of complicates the picture a little bit. You can just find these angles, these exact values. This is the best way to solve it. And to remind us what makes inverse functions tricky, let's go back to chapter 6, inverses, where we solved a problem very similar to this one right here. So just to take a look into something similar from before, we calculated sine inverse -3/2. We calculated this, sine inverse 1/2. If you took sine inverse here on the left-hand side, you'd be taking sine inverse 1/2, and you would have gotten the pi over 6, but it's not the full story. The trouble with the inverse function is it's a true function. There's exactly one output to every input. But we have multiple solutions when we go to solve the sine function here. So even though they're related problems, sometimes you do want to think about the inverse function. If this was, say, sine x equals 3 points, no, not 3.7. If this was sine x equals 0.37 or 0.56, so it's actually between -1 and +1, now we do need to use the inverse function. Will give us one angle, and we have to use other trickeries to get the other angles. So that's going to be the last things we're going to do in these notes. But one more like this, finding all solutions in the interval 0 to 2 pi, where we can find the exact values like this one down here. So let's take a look into one more similar kind of problem. Determine all solutions to the trigonometric equations. That should be singular, equation. I think I have to make that edit on the rest of them. To the trigonometric equation, just the one equation, in 0 to 2 pi. And here's our equation. It's got a lot going kind of wrong with it when you look at it. There's multiple trig functions, both cosine and sine. The inputs are different, 6 theta, 7 theta. So it looks like kind of a nightmare when you look at it. Let's think about this one. There's an identity that we could use. Anyone happen to spot a good identity for this problem?
Some difference identities, isn't it?
Yeah, good eye. So it looks really, really bad on face value, but it's in fact, just as you said, one of these identities. Let's pull it up just for a refresher visualization for everybody. These notes kind of start off in the most awful way, doing a big derivation. But here's the good stuff. Here's all our addition difference formulas for sine and cosine. Because it goes cosine, cosine, sine, sine, it means we're really looking at the last two down here. There's a positive in the middle, so that's this one, the very last identity. We'll just turn into cosine alpha minus beta. So a lot of the ways we use these identities is mainly just pattern recognition, knowing that this just had the right format because we've seen it before. And the only way to really get that experience, to notice that that's something you've seen before, is to just constantly write down this identity. If you're about to use this identity, to memorize it, to prepare yourself for exam 3, to help with your pattern recognition, just write it down. And it has a way of just getting into your subconscious bit by bit. So the identity goes cosine alpha. This is the nasty one where the sign changes in the middle. Minus beta is cosine alpha, cosine beta, plus sine alpha, sine beta. So now that we have the identity down, the alpha in the problem is going to be 7 theta, beta is going to be 6 theta, and this entire left-hand side becomes cosine 7 theta, plus here is always good to be careful with, goes to minus 6 theta. That's just the alpha minus beta part that we see up here in the identity. So cosine 7 theta minus 6 theta equals 1/2. That means this problem is one we could have done as example 1, but it just seemed like a nasty one to start off. It's cosine theta equals 1/2. And that's all we're solving on this one. So humongous reduction in complexity the moment we spot the identity that we needed to make that happen. The rest of it is the same kind of steps. We have a trig function isolated, drop down a unit circle diagram. We have 1/2 we're using on the positive x-axis. We need to know how we get there. So go up to this angle. This one is at pi/3. Then go down to this angle. This one is at 5pi/3. And that's the set of solutions. From here, we can say theta equals pi/3, comma, 5pi/3. We just stopped because we're only circuiting between 0 and 2 pi on this one as well. Well, we did it, folks. This one looked really bad, but it was just kind of a refresher on a trigonometric identity. If you're thinking in terms of inverse functions once again, we did something pretty similar to this one as well, I believe. Let's take a look. Let's scroll through. Let's see, cosine inverse -1, and there it is. You can calculate cosine inverse of 1/2, but when you do that, you only get the one solution. Oh, hang on. Too many windows open. You only get the one solution, pi/3, that we saw here. If you had that one solution, pi/3, you need to use some method to get the other solution, 5pi/3. Those are the things we're going to be looking into then with the next two sets, where we really do have to use an inverse function and find all the angles in 0 to 2 pi. Well, these are the main techniques. The next two examples, I only have two versions we're going to take a look into. I think they're important problems because when it comes to solving trigonometric identities, there's no guarantee that this has to be a half. It could have been a 1/3, right? And if it was 1/3, now we have to work in a different way. We really need the inverse function. So those are going to be the next grouping of problems we take a look into. Let me minimize some of this stuff. Any last questions or comments before we try out another? Okay, so here's our next one to try. We're going to use our calculator this time to solve this one. But first, let's get into the format where we would be using that calculator in the first place. Common calculators are going to be the TI-30XA, the TI-30X2S is a great choice as well. And I'll show what these steps look like on this calculator here. We'll just make this our official calculator to demonstrate with. It's kind of weird. It's easy to emulate a TI-84, but that's not a really nice thing to do in this class because it's not allowed in an exam setting. And this calculator is really hard to emulate. So I felt like a screenshot is the next best thing. So here's our calculator we're going to be using on this. One piece of advice is we're going to be using calculator more and more in chapter 8 and these problems right here. So I would stick with the calculator you know you're going to use in homework, that you know you're going to bring into the exam setting. So that way everything feels familiar when you go to use these same kind of steps. So first thing we'll do before we even begin to use a calculator is make this one trig function. We have a sine x and a cosine x, and that's no good to us. But, here's a really cool trick. If you need to make this one trig function, you can just take 3 sine x equals 8 cosine x, and just divide that whole thing by cosine x. If you do that, you have a cancellation on the right. But on the left-hand side, sine x divided by cosine x is tangent x. So now it's 3 tangent x equals 8. Divide by 3, and tangent x is 8/3. And that's a really weird value. Nowhere has this come up in our notes so far. We've found tangent x equals things like, say, √3 or negative √3/3, stuff like that. Or maybe a positive one, negative one, but not this. This one's weird, 8/3. There's no nice angle that takes us to 8/3. So that's why the instructions are saying round to 2 decimal places. We need a calculator this time to make this work. So here's what this is going to look like on the calculator. First, let me wipe out this stuff. Back over here, what the algebra looks like is you take tangent inverse of both sides. So it goes tangent inverse of tangent x equals tangent inverse of 8/3. And the reason we take that step is back here in the inverse function land, let's scroll to something similar. There's a particular cancellation that happens with the function and its inverse. Here's the more common cancellation, or hang on, don't think we have it on here. I have it just in one direction, tangent with arctangent. It also cancels in this direction, tangent inverse with tangent x here. So once you do that cancellation, it's gone now, and you have x equals tangent inverse 8/3. But we need to find that value. So let's compute that next. First thing you have to do in your calculator, though, is make sure it says rad right here in this particular calculator. Otherwise, you're getting something in degree mode, and we're expecting a radian angle measurement for these kind of problems here. So set that to rad. You can use this button right here to toggle. DRG just stands for degree, I think. Hit it once. You have a little cursor options that can toggle between degree measurement and radian measurement. So put it into radians, and the calculator is going to work the way we're doing things normally. And now your inverse function is right here. But you can't hit the 10 key. You have to access the function that's printed above it that says tangent inverse. So hit the second key first, then the tangent button, and you should see something that looks like this. Tangent inverse, then type in 8 divided by 3, and you should get a value out. Here's what it would look like in Desmos. Let's clean this up a little bit. Desmos doesn't have a tangent inverse. It has an arctangent, is the function that they printed as. I mean, that is tangent inverse. We put in 8/3. And this is the angle in radian measurement that we're expecting. To 2 decimal places, as it says to rounding, the solution x is 1.21 radians. So x equals 1.21. I'll put here just as an emphasis, this is in radians, because we're used to seeing things like pi over 6, pi over 3. And that's what you would get on the output here after hitting enter. But that's one solution, and there is another one. So let's find that other solution. First, any questions at the moment with the calculator? Anyone getting something different, or are we getting the same result? Okay, now here's the trick to get the next solution. We're looking for solutions in the interval from 0 to 2 pi. So 0 up to 2 pi. And if we found 1.21 radians, you know it's not easy to plot that necessarily, but you can convert this angle, multiply it by 180 degrees over pi, and it tells you it's about 70 degrees. This gives you a good read of where it is. It's somewhere right around here. So this is the x equals 1.21 radians. Now we use periodicity. Recall the period of tangent is period equals pi. That means tangent x plus pi is back to tangent x. So if you happen to put a 1.21 radians right here and add pi to it, you would get tangent at 1.21 radians, which checks back, giving you the 8/3. So that's the idea. Take the 1.21 radians, add pi to it, now you're down here, and that's your next solution. So here's 1.21 plus pi. Also in radians, let's throw that into the calculator. X is 1.21 radians, or 1.21 plus pi radians, so 4.35 upon rounding. Let me connect the thoughts here. This is where the 4.35 came from. And we wonder, can we keep on adding pi? Well, if you did it again, I have too many tabs open. If you add pi again, you end up at 7.49. And the trouble with that is you're only looking for solutions between 0 and 2 pi, and 2 pi is 6.28. So add pi one more time, and we've rotated back up here, but we're beyond 2 pi at that point. That means there's just two solutions, 1.21 radians, 4.35 radians. And we can check this as well. Take a look into the number 8/3. Take tangent. At one candidate, 1.21. And you know what? That's pretty close. Keep in mind, we rounded the radian measurement here, so we're not getting exactly to 8/3, but that's sufficiently close to almost to 100th for me to say we've got the right value there. Plug in the next one, 4.35, and that's sufficiently close as well, within 100th. If we rounded to 3 decimal places, we would have been even closer. So that's the world of solving trigonometric functions using the tangent inverse function. It's also the reason why we didn't quite do that in the last problems. It's easier to just spot the angles rather than using these kinds of tricks to find the next ones. We'll practice this one more time when we return next class, looking into the version for cosine. But any last questions or comments at all, folks, before we call tonight? Yeah.
Does that mean that variable tan function, you only ever have two results, two solutions, never more or less than two?
That depends. So if this was sine 3 times sine of 4x, h times cosine of 4x, and you're solving tangent of 4x, what you've changed now this time is the period. So this would repeat a lot of times between 0 to 2 pi because it has a different period. So let's see if I can plot that really quickly. Here's tangent x. This one only has two solutions. But if you're dealing with tangent 4x, then there's potentially many solutions. This is kind of hard to zero in on. Let me change my axis to 0 to 2 pi. So in blue, this is what we're looking at if we're dealing with just, oh, I shouldn't zoom out. This is what we're dealing with if we're looking at just, say, tangent x. But green has many repeats over and over again because the 4 here has changed the period from pi to pi over 4. So this is a way to get more than two solutions. You have to change what the x was to something like a 3x, 5x. Then you have tangents, say 5x again, and potentially loads of solutions you'd be hunting for in there. Does that make sense with that question?
So I have a follow-up.
Yeah.
How does the input of the function relate to its period?
So the input here, gotcha. So the relation between those two is if you have, say, tangent equals, let's say, just an ordinary bx, then we could say the period is pi divided by b in that way. If there's a little bit more, say like plus c, then that'd be affecting its phase shift instead.
Right.
Other questions so far about that? Okay, well, those are really good follow-up questions. Those are the exact kind of questions you want to ask about this kind of setup. Solving trigonometric equations has lots of concepts that can come all together. So we'll return to these notes when we come back next class. And maybe just some parting reminders. Best way to study for these upcoming exam 3 is to definitely solve those problems. I'll try to get your solution sent back as soon as possible. And if you have any questions that are coming up while you're studying for this exam, don't hesitate to reach out. Monday is the official day that we'll take the exam, but if you have any conflicts in your schedule when you go to schedule it, you can take it in a later day in the week, much like the other exams. Also, it means we're not going to have class next Monday since you're only on the hook for, say, 2 50-minute sessions per week, not 2 lectures and then another 50-minute exam. So just like exam 1, exam 2, won't hold class officially next Monday. We'll be back at it a week away from today. But have a great night, folks. I'll be happy to help out if you have any further questions. Thanks. Have a good one too.